houses, they put the studs 2x4 different ways depending when they're putting joists in. Joists are always put that way or that way because they bend. And in fact, building codes where you put windows and doors stipulate the size of the wood you have to have in that direction across the gap to carry the roof load, etc. And then leading on from that to the argument. While we're at it, because box beam came up, here's a box beam. What's happening now is these side panels are in shear. If you have just a strip of wood, although just bends, there's no strength that way, whereas that way has got strength. When I do that, I'm putting what's called shear forces. I'm trying to make it slide. A box beam simply has two side walls which are in shear. That's giving it strength. These two pieces are giving it strength in the other direction. And the overall structure also resists twisting. It's got a good torsion strength. These are the reasons behind building bridges with box beams rather than solid beams, or with I-beams rather than solid beams. It's very simple physics, it's moments and forces.
And you probably know, can you hear me okay without the...
Yes.
Yeah, okay, good. We'll keep it that way, and if I drop off, just give me a signal. You've all seen these oriented strand board wooden I-beams, and that's pretty common now in house construction. Now we also have the issue of, so we have the issue of forces, now we have the issue of what shapes are best suited to withstanding those forces. We have a couple of
This is another
have some classical ones here. We have the square.
What we've done, we figured that this is nice, but it'd be much better if you had something the kids could actually play with, so we built these. I'll have to climb on the chair and put it up high, so as you can all see. We start with a square. That's no rigidity to it. If I put cross piece in, it now has rigidity. More rigidity that way, this is flexing stuff. But because the end are fixed to this, it doesn't have it that way. But we now put a cross piece the other way.
With your box beam,
is it the welding points that give it its strength? Because it's in the shape of a square or a rectangle.
In terms of Mr. B, if this was a way, yes, if these weren't here, you're relying on the thickness of the material, yes, and the weld there to stop it going that way. Which is why quite often in box beams they have either struts or complete diaphragms with intervals down inside the beam.
Which serve as,
Yeah.
which serve the same purpose.
Or they'll bring the top plates over, out, top of the back wall, and put a web on the outside, same purpose. Now the other shape, look at, it's in that animation as well, it's the arch. The arch has some strength to it, but this is the Roman arch, the original arch. What it really depends on, it has to have structure here to stop those sides flexing. So when you look at Roman arches, you normally have two of them together with masonry between, and that's giving that strength. This arch on its own will be floppy. But when they built medieval cathedrals, then they ran into this problem because up to then churches, you had lots of arches with lots of pillars. It wasn't a big open space. And then someone, an engineer obviously, had this brilliant idea of, well, supposing instead of doing that, you made it more pointy. This is your Gothic arch. And now, because this is more vertical than this, you're getting more compression. Here you're getting compression, but at this point, the force is acting down this way. Instead of just here, whereas with this arch, more of the force is going to the wall. And it's a more rigid arch. In a sense, they can make it bigger than the vaulted ceiling. That's the whole key to the Gothic arch.
And what did they do to compensate for that flex in that Gothic arch? Anybody remember? Flying buttresses, yeah, exactly. Oops. Gotta do it from there.
Talk about triangulation before we get to arches, it's okay.
Well, here are examples of triangulation or triangles in everyday life. I mean, everybody sees the trusses that get built. There are other structures. You can see basically rectangular structures, but with triangular truss work inside. There's another one. You see it from the other direction. See it from the other direction here. Playground equipment, all triangulated, and we even have one right here. I think this could hold probably a 100-pound camera.
It might, but I tell you, 50 is supposed to be.
Okay, here's an example of a beam structure. You see the rectangular outline, and then the triangulation in both directions. And this is a pretty simple one. So this is, and some of you may have made these. Anybody done a stint with Habitat for Humanity where you go on a weekend and build, yeah, I know you have. You'll build a lot of these. And that's because, as we've seen, that beam winds up being very strong because of the triangular construction. These are known as trusses. The truss is very strong, and it's much lighter than a solid beam would be. I mean, you can make up solid beams to span those big dimensions in a house, but they are very expensive. Things like glulam beams, and in the old days, of course, they made them out of a single tree, right? You could get beams that were 20 inches thick and 10 inches wide to support a house structure. Can't find those anymore. And trusses wind up being used not only in house construction, but in virtually all bridge construction. No matter what the basic structure is, you'll find sub-elements of it that are triangular truss structures.
Look above your head.
Yeah, there you go. You can see we got tons of it running across here. Very lightweight, in this case, steel construction with triangular, looks like 1 inch or so rebar. There's another example of a house truss made from 2x4 studs. Lots of different shapes and varieties, but you see the thing they all have in common. The thing they all have in common is that triangular structure. I have an old shed that I was redoing, and basically the roof was basically like this, and it never, well, it occurred to me that I had to deal with the snow in the wintertime on that structure, but it didn't occur to me that I had to deal with quite as much snow as it happened. And that structure, like that, collapsed. We went back and redid it like that, and it's been very good ever since. Here's a typical bridge from the early part of the 20th century. They're still building them like this. You can see all of the truss work here in the top and along the sides. What basically is a beam bridge with truss work. Can't tell whether there's truss work underneath it or not, but you can see it here on the sides and the top.
Note the last bullet. Very important. You're going to be building a truss bridge. And the last time we did this, people forgot that last bullet.
And again, lots of varying designs for truss bridges. They all have names of, I don't know, John, are these names of engineers who were involved in the design? And I'm sure you've all seen examples like this. Actually, my favorite isn't actually shown here. Any of you ever been back in upstate New York along the Old Erie Canal? There's a great bridge back there that looks like a beam bridge like this one, except it's upside down. And when I asked the question, well, why was it built that way? I was thinking, you know, some amazing, you know, engineering breakthrough that somebody had made. The reason it was built that way was because when the Erie Canal was built, it was competition for the only way at that time that they had for moving goods back and forth. It was competition for the wagons. So they built the bridge upside down so that only small boats could get through. And that bridge is still there.
Thus the words to the song, "Low bridge, everybody down."
Low bridge, everybody down,
everybody down.
yeah. Outside of Lockport, New York, that bridge is still there. Here is a cantilever bridge, and in this case, you know, like a cantilever, like a diving board. So the bridge is supported in the middle of the span with